Hello guys, in lecture 7, I'm going to introduce different types of methods for image enhancement. It's called lecture 7, but actually I'm going to use 2 weeks. Or you can say if we were using in-person teaching method, 2 meetings to finish this chapter or say this lecture because the content of this part is relatively hard to understand compared to other lectures we have finished. And it's pretty important. Image enhancement is important, and the next topic, which is image classification, is also important to remote sensing. So I would suggest um, after watching the videos, if you're confused, read the textbook, and one there are also labs for this. I mean, labs for image enhancement, and next one, lab for image classification. Um, Finish these labs carefully and ask me questions using email or um, participate the class at the office hour. And if you have any questions, just ask and read the textbook. So it will be, say, less difficult for you to understand the content for image enhancement and image classification, which is lecture 8. Okay, today let's start um, the topic of image enhancement. So specifically, there are 3 types of enhancement. So radiometric enhancement, spatial enhancement, and spectral enhancement. Okay, in the first part, or we could say in the first meeting or in this week's meeting, of course, virtual online meeting, I'm going to finish the radiometric enhancement. And the spatial enhancement and spectral enhancement is for next week. Okay? So radiometric or contrast enhancement, enhancing images based on the values of individual pixels by manipulating bright value histograms. So in other words, when we're talking about contrast enhancement, we are going to um, address something called bright value histograms. Okay, you may have learned the concept of histogram in statistical class. Okay, but here we're also going to use it to do uh, image enhancement. And the spatial enhancement is enhancing images based on the values of individual pixels and their neighboring pixels. A spatial enhancement can also be considered as spatial filtering. Okay, we're going to create different types of filters. Okay, of course, software filters, not a filter in the real world or something like that. Okay, spectral enhancement is enhancing images by transforming the values of each pixel on a multi-band basis. Okay, for this week, contrast enhancement is what we're going to learn. Okay, so expand the original input brightness values to make use of the total dynamic range or sensitivity of the output device. What does it mean? Let me show you an example here. So on the left side, we have a remote sensing image. Okay, in this image, we have island here, right? And this is another land on the left side, and bottom left there is another land. Okay, and these 3 lands, this island and other 2 lands, they are separated by a river and I suppose another huge river, and I think this is ocean. Maybe this is Manhattan. I'm not sure. I'm not sure, but you can see that in general, this image has a very dark tone, which means that all pixels they are very dark and they are very difficult to differentiate. If you want to differentiate them, okay, it's hard because all of them they're relatively dark. Okay, so why is that? If we are looking at the histogram of this image, we will know why. So this is a very simple example of image histogram. So the horizontal axis is for brightness value, or you can consider brightness value as pixel values. Okay, so from 0 to 255, usually this range is the total dynamic range of all screens or devices that can display images. Usually that's the case. So from 0 to 255, which means that there are 256 values, right? Because there is 0 to 255. Okay, so this is the whole range. Okay, and the vertical axis is the frequency of pixels. If the frequency value is 100, then it means that there are 100 pixels in this image with a specific brightness value. So image histogram is something to address the relationship between brightness value and the frequency of pixels with specific brightness values. For example, here, there is a huge spike here, right? Huge spike here. What does it mean? It means that a lot of pixels in this image, they are having very similar brightness values because the spike is very thin. It's within a very small range, and a lot of pixels, they are having a value within this range, within this very narrow range. And this value is pretty low. I think it's 10 or something, right? And then there are other pixels with higher brightness values, right? Because we can see here is a small spike and another hill here, okay? But in general, we can summarize two things from this histogram. Firstly, a lot of pixels in this image, they are having similar values, and these values are pretty low. That's the reason why this image looks very dark. Okay, of course, there are other pixels have relatively higher values than these pixels within this small range. But again, even they have relatively higher values, the absolute values of them, given the whole range, the whole total dynamic range, their values are still very small. It's far below 128, which is the half of the whole range, right? So two things. Firstly, a lot of pixels, they are having similar values, and these values are very low. And for the whole image, all pixels, their values are clustered within this very small range. And this image does not take advantage of the whole dynamic range of the device, of the whole brightness value range. Okay, so we're going to use radiometric enhancement to address this problem. We're going to try to make sure that pixels in this image, they are having different values instead of what? Being clustered within a very small range. And we're going to try to make sure that this image makes good use of this dynamic range from 0 to 255 instead of using only a small part of the dynamic range. So as a result, this image will be brighter and pixels will be easier to be differentiated from each other. Okay. So we have different methods to do this, to redistribute, to manipulate the histogram. We have linear methods. We have nonlinear methods. Okay. Sometimes we call them linear contrast enhancement, or we simply call it linear contrast stretch. Why stretch? What is it you want to stretch? I want to stretch that histogram. Okay, so linear contrast stretch or nonlinear contrast stretch. Okay, under linear category, we have min-max contrast stretch, standard deviation contrast stretch, and also piecewise linear contrast stretch. And for nonlinear method, we have histogram equalization. We have logarithmic contrast stretch. I'm going to introduce them one by one, and they are what I want to introduce in this week. And like I said, spatial enhancement and spectral enhancement, they are the content for next week. Okay, let's start with very basic method for linear contrast enhancement, which is called maximum contrast stretch. The idea here is very simple. Okay, we're going to use the mean value and the max value, okay, in the image to standardize the value of each pixel. So the equation is here. So BV out, which is the output brightness value for a pixel. Okay, so BV out is something we want. BV out is the output value for a specific pixel in your image. And we're going to apply this process, or say this minimum maximum contrast stretch, to all pixels in an image. So a contrast stretch is a process of what? Not of, for all pixels, see that. Okay, we're going to do it pixel by pixel. So BV out is the output value, is something we want. BV in is the original input brightness value, or the pixel value before the enhancement. So quant K here is the range of the brightness values that can be displayed on the CRT or on any screen. CRT is a very old type of screen. We don't use it today, but it's from the textbook. But let's just call it screen, or simply CRT. Usually, this value quant K is 255. Okay, zero, you can just, for now, ignore it, okay? Okay, and min K is the minimum value in the image. Okay, in the original image, the image before enhancement, and the max K is the maximum value in the image. Okay, so let's talk about this mathematical equation a little bit. So the denominator is the difference between max and min values of the original image. And this difference here is used for normalization. Normalization of what? Normalization of the difference between each pixel's value and the mean value of the image, of the original image. And when we finish this you can say standardizing process or normalization process in this bracket. After that, we multiply that standardized value by what? By the range, by the dynamic range of your device. Okay, so here is the equation. So this is the original histogram we just saw, right? Here we use another, how can I say, another chart here, okay, to show you the process of min max contrast stretch. So here in this chart, or in this figure, the horizontal axis is for what? Is for the pixel values of the input image, or the original image. So you can see here is B min, here is B max. Okay. So you can say the dynamic range of this original image is very narrow. It's between B min and B max. And Y, or vertical axis here, is for the range of the output image. So X is for input image, Y is for output image. For input image, the dynamic range is decided by B min and B max, and we want to stretch this small range to a much larger range between 0 and 255. So input is X, output is Y. The range for the original image is addressed here by B min and B max. The range of pixel values of output image, or the image after enhancement, is addressed by Y, is addressed by the difference between 255 and 0. So this small range here is for the input image. The large range here from 0 to 255 is the pixel value range for output image. So now you can say the idea, the reason why it's called stretch. This small range has been stretched in the output image. Okay. So for example, the mean value of an image is 4. Of an original image is 4. The max value is 105. We want to stretch this range to 0 and 255. Okay, here is the example. So in the original image, if a pixel has a value of 4, it will be processed using this equation, right? BV in is 4, mean value is 4, right? Mean value is 4, max value is 105. So 105, 4. You just need to replace all this input here by specific values, right? And multiply quant. Quant is 255. So after the enhancement, that pixel with an original value of 4 now has a value of 0. Okay, so similarly, you can do this for another pixel. For example, if that pixel has a value of 105, which is the maximum value for original image, you do the same thing. You will say that after the enhancement, that pixel will have a value of 255. So that pixel with mean value of 4 after the processing still has the mean value, but that mean value is not 4 anymore, it's 0. And another pixel with an original value of 105, which is the maximum value of the original image, now still has the maximum value of the output image, but it's not 104 anymore, it's 255. So you can say this process is very straightforward. Every pixel will be rescaled from a range from 4 to 105 to another range, which is from 0 to 255. So this linear enhancement process, or specifically min max contrast stretch process, is a projection from original brightness value range to another range you want. Okay, it's just that simple. Okay, so another example here, right? For specific band K, for an image, there are multiple bands, right? For a specific band, BV in, which means the original brightness value is from 4 to 104, right? So this is a histogram of the input image, right? And we want to stretch the histogram from within the range of 4 to 104, okay? To stretch this segment, okay, to what? To another range. That range is from 0 to 255. 155. So 4 to 104 has been stretched from 0 to 255. So on the left side, we have the histogram of the original image or input image. On the right side, we have the histogram for the output image. If you compare them, the histogram for the output image is wider because the brightness values of all pixels in this image, they have been widely distributed from 0 to 255 instead of being from 4 to 104. So you can expect that in the output image, the brightness values are distributed in a wider range. So pixels, the grayscales will be, there will be more grayscales used for pixels. So pixels can be relatively easier to be differentiated from each other. Okay, so the contrast has been enhanced. Okay. The more pixel values we have in an image, the higher the contrast of the image. Okay, so let's see the result. So this is the image we saw before, right? That's a histogram of that image. After the maximum mean maximum contrast stretch, you can say the histogram has been stretched. Okay, so you can say brightness values in the output image, they are within a larger range. They are within a larger range. And for the image, we can say the obvious difference here, right? Obviously, this image is brighter, although, water body is still very dark, okay? It's very dark, should still be 0, okay? But you can say all those pixels on this island, on these two lands, they are having more grayscales, which means the brightness values of them are distributed in a wider range. So we have brighter areas, darker areas, and they can be differentiated much easier compared to the input image. So this is a direct result. You can tell the difference here. Okay, so that's the reason why we wanted, or say we did the histogram manipulation. Here is the result. Okay, so obviously we can get more information from the image on the right side than the image on the left side. Okay, so that's mean maximum contrast stretch. It's a very fundamental one, but the idea here is very important. We rescale original pixel values, or we project original pixel values to another range, from a narrow range to a wider range. Okay. So the next method here is also linear, but we do not use min and max values to do the stretch. We use standard deviation to do the stretch. So mean and standard deviation, they are very fundamental concepts in statistics. So mean and standard deviation here in the context of remote sensing image, they are mean and standard deviation for all pixels in one image. So in order to calculate mu, or mean value for an image, you need to calculate the sum of all pixel values and divide that result by the number of pixels in this image. That's mean, right? Standard deviation is more complex, but here, again, xi is for the brightness value of a pixel. X bar is the mean value of the whole image. N is the number of pixels in that image. And standard deviation, what's the importance of that? Standard deviation is a quantification of the variation of a group of data. For a specific remote sensing image, if the standard deviation is very low, it means that the brightness values of pixels in this image they do not change a lot around the mean value, which means the variation of pixel values, the variation of the pixel value in this image is very small. If the standard deviation is pretty high, it means that the variation of pixel values in this image is very strong. Okay, so this is the equation we saw before, right? For min max stretch, linear stretch. And here we do some adjustment. So BV out doesn't change, BV in doesn't change, but min value and max value are not employed here. Instead of that, we use mu minus standard deviation to replace mean value. We use mu plus a standard deviation to replace max value. That's it. That's all you need to know about standard deviation contrast stretch. And here specifically, we call it, for this specific equation, we call it one standard deviation stretch, which means that you can replace this standard deviation to 2 times of standard deviation, or even 3 times, or even 4 times, but it's not necessary. But you should know that this equation here is for one standard deviation linear stretch. You would ask, why do we want to use 1 time of standard deviation or 2 times standard deviation? Because they're convenient. Why? Because on the left side, we have 3 figures to show you why we want to use standard deviation for convenience, not only in remote sensing image processing and enhancement, but also in all areas that can be addressed by statistics. For example, here, as long as your data set follows normal distribution, the histogram of your data set should follow this bell-shaped histogram should follow this bell-shape or histogram or distribution, say that. And for example, if your mean value is 0, right, and you can calculate the standard deviation, mean minus 1 time standard deviation and mean plus 1 time standard deviation, and this area is addressed by this shade here. And each side accounts for 34% of your data set. Okay, if you are using a -2 standard deviation and +2 standard deviation, the area between these two measures, minus and positive 2 times standard deviation, this area accounts for 95.4% of your data set. This is very convenient because we don't even need to know specific values or specific numbers of observations in your data set. As long as your data set is following this normal distribution, which is the most widely used distribution anywhere. Most, I would not say most phenomena, a lot of phenomena in our society, in our world, when we're talking about data sets to address this phenomena, these data sets, they're probably following normal distribution. So mean and standard deviation together, they gave us a very accurate, not very specific, but accurate distribution of your data. Okay, so as long as you have mean value and standard deviation, you know that 68% of your data set or 68% observations in your data set, they are within the value between what? Between mean minus 1 standard deviation and the mean plus 1 standard deviation. So we can simply use standard deviation to do the linear contrast stretch like this. Okay. So when you're doing 1 standard deviation stretch, this is the area, right? If you change this from 1 standard deviation to 2 standard deviation, this is the case. If you change it from 1 to 3 times standard deviation, this is the case. Okay. Yeah, how about 2 times standard deviation stretch? You simply change this standard deviation to what? 2 times standard deviation. Okay, so that's it. So another example here. Okay, so similarly to the max min stretch, here we have the mean value for your histogram. We have the mean value for your histogram. We also have the minimum and maximum value for your image. But here, I'm not going to use mean value and the max value to do the stretch. We use what? We use mu minus 1 and mu plus 1 standard deviation. These two measures to do the stretch. Okay, for example, the mu minus 1 standard deviation is 12. Okay, mu plus 1 standard deviation is 43. So we want to stretch. We want to stretch the values from 12 to 43. We want to stretch this narrow range to a wider range from 0 to 255. Okay, so here comes the question. What about other pixels who is outside mu minus 1 standard deviation? And how about all other pixels who have the value larger than mu plus 1 standard deviation? In other words, how about these pixels? Right? How about these pixels between minimum value and mu minus 1 standard deviation? How about other pixels with values between mu plus 1 standard deviation and max k? Okay, so here is what you do. If that pixel is within this range, you can just simply give them 0 for values in output image. And for other pixels outside this range, but these pixels, they have larger values than mu plus 1 standard deviation. In the output image, give them value of 255 because these two groups of pixels, they are simply not within this range. We want to do the stretch. Okay. So from 12 to 43, that's from mu minus 1 standard deviation and mu plus 1 standard deviation. Okay, 12 to 43. All pixels with values between these two values, they are assigned a new value between 0 and 255. And for all other pixels outside this range of input image, they are either assigned 0 or assigned 255 in the output image. Okay. So let's say this again. Original image, original histogram. When we're using 1 standard deviation stretch, you can see that the histogram here is not the same anymore, and there was even larger change than after the max min stretch, right? So now you can say the whole dynamic range has been used by this output image, and here is the result. Okay, so now it's even easier to differentiate land and water body. Okay, some pixels, they are becoming even brighter than before, than the output image of max min stretch. Okay, of course you would ask, which method should I use? Right? I have introduced 2 methods, but I'm going to introduce more. So which one should I use in my research, in my work? there is no correct answer, quote unquote, correct answer for this question, okay? In your research, in your work, you may want to try different methods, okay? And to see the result and say which one is proper or appropriate for your illustration, for further research, for further enhancement or classification, okay? But you should know once the enhancement has been done, okay, the image you have is not original image anymore because pixel values have been changed, okay? And next one is something called piecewise linear contrast stretch. But I will introduce this part in the next video. I will stop here for this video, and I think another one video will be good enough, okay, to finish this week's content. Okay, I will see you later. Thank you.